All right, so today we're going to keep working in this idea with this idea of differential equations, and the first question is actually one that looks just like you were working in the last section. So the first question that we're going to look at says we've got dy dx equals 6 minus x. So a reminder, a refresher, how do we do this problem? What do we do? Okay, so we're going to first write this as dy equals 6 minus x dx. I'll put this in parentheses just to indicate that. Now what? Integral on both sides. Good. So what does the left side become? Y. And the right side? X squared over 2, right? Yeah, and then plus c. Okay, so that's just a reminder from last time. That's where we sort of ended last time, was in looking at problems that did this, right? All right, so we're going to pick up from there and do another one with the same kind of directions, but it's a little bit different as it starts out. So there's actually a couple of differences. So somebody tell me what you see that's different about this one as it starts out. It says y prime, but that's easily fixable, right? You actually had some homework problems where there was a little bit of that going on. There's something else about this one that's different. There's an x and a y on the right-hand side, which is a little different than what we've had before, right? All right, so as we do this, let's first change that y prime to dy dx. And we have this written, and it's actually written in factored form for a very good reason. Because what we really want is we really want everything with y on one side and everything with x on the other side. So that's what we're going to do. We're going to multiply that dx over there just like we have been, and we're going to divide the 1 plus y to the left. Does that make sense? So the left-hand side actually ends up looking like 1 over 1 plus y dy equals x dx. Okay, so does everybody see where all the pieces went and why? Okay, so now we integrate. But the difference, of course, as we integrate is that on the left-hand side I don't just have dy, do I? But that's okay. What's the integral of 1 over 1 plus y? Natural log of the absolute value of 1 plus y. And how about on the right-hand side? Plus c. Good. Do you think we're done?
Does the other side need a plus c too? Or?
Well, we could put it there, but it wouldn't be the same c. Okay? So, yes, we could put like a C1 over here and a C2 over here, and we could somehow simply move the C1 over with the C2. But it sort of is overkill. Eventually there is a constant this can differ by, so I really just need to put it on one side or the other. It's kind of like, you know, when you had, well, let me use the previous example. When we took the antiderivative right here, I could say that this is 6x plus C1, and this is x squared over 2 plus c2, but in the end, I'm just going to actually add those two constants together anyway. Make sense? And that's a really good question because we're going to see something happen, even in this very problem that we're working on, this one right here, where you're going to see something a little bit different happening here, okay? So with those constants that you're actually mentioning. All right, so at this point, we're right here, but we're not done. Why are we not done? Because we didn't solve for y. And the problem did start out with y prime equals, so if we are able to solve for y, we want to do so. What would I need to do in order to solve this for y? Say that louder for me, Taylor.
Do e on both sides.
Right, and we could actually use each of the sides as exponents for e. So I'm going to put an e down here so that each of these are the exponents on the number e. Why do I want the number e? I mean, how's that going to be helpful?
E and the natural log cancel.
E and the natural log cancel. That's exactly right. So the left-hand side then simply becomes 1 plus y. Right? The absolute value and, not the absolute value, the e and the natural log cancel out. The absolute value is not necessary any longer because we've eliminated the natural log that it was there for the purpose of being there. Now here's the interesting thing that happens on the right-hand side. You have a property of exponents here because you have base e. We have this exponent with addition, right? Well, I could actually write that as two separate bases with their own exponents. Agreed? Is it okay? Now, just for the sake of what I want to do in a moment here, let's go back and call this C1. Okay?
Are they multiplied together?
Yes, these two bases with the e's are multiplied together. So we're basically using that property in reverse. We have a property that says a to the m times a to the n is a to the m plus n. Do you remember that property, Parker? So we're kind of starting on the right-hand side, and we're moving back to the left-hand side of that property. All right, so here's why we like this. Okay, e is a number. C1 is a number, so e to the C1 is a number. It's just some number, right? In fact, it's a number that I'm going to give another name to. I'm going to call this number C, which is why I went and changed that to C1. I know it was tricky. All right, so I can actually write that as a constant written in front of the e to the x squared over 2. And then I can move the 1 that's on the left to the right-hand side. So this is y equals c e to the x squared over 2 minus 1. And you're going to see this trick, sort of, if you will call it a trick, used throughout this lesson. This idea that I can change something that looked like addition over here at this point into something that in the end looks like a multiplication factor. It's easier to work with when it's a multiplication factor, and you'll see why as we keep working, okay? Any questions on this one? We did a couple of new features here. Okay. The next problem is going to take you back a little bit into college algebra because it has some phrases in here. This phrase varies. Do you remember that phrase from a college algebra 2, 3 kind of course from high school, something like that? All right, so this says the rate of change of y with respect to x. So let's start there. What does that phrase mean? What is the rate of change of y with respect to x? What does that mean? It's what? It is. It's dy over dx. That is one of those phrases that in Calc 1 you learned means derivative. That's all that is. Okay, so that's not the college algebra part. This part right here is the college algebra part that I was wanting you to remember. Varies jointly. What in the world does varies jointly mean? Anybody remember? Well, it means that we actually have the two values that it's varying jointly with respect to as multiplication factors with a constant potentially thrown in. There they are. So you have, there's three phrases back in college algebra. In fact, let me pause and I'll write this over here on the side. I'm going to need my space in a minute. But there's three phrases from college algebra. The first one was varies directly. And you ended up, oops, there's an L missing. And then you ended up getting something that looked like y equals cx. So if x increases, y increases. If x decreases, y decreases. By a factor of c, right? So c may be 2. So it may be that as x increases by 1, y increases by 2. Okay, so as x increases or decreases by some number, it is directly corresponds to how y changes. That's varies directly. The second one you had was varies inversely, and I think we may have an example of that later in the lesson. I can't remember. What does that phrase inverse mean to you? There's a key word that does this. Reciprocal. There's an idea of a reciprocal when we look at inverse here. So let me write down what it ends up looking like. It ends up looking like this as an equation. So the idea being that if x increases, y decreases. That's what inverse variation does, is that as one thing goes up, the other one comes down. And we see inverse variation in pricing things all the time, right? As prices go up, demand goes down. People don't want them. And then we're about to hit Black Friday, right? And the prices go down and the demand goes up, right? So this is an inverse variation that we see all the time. And then the third one's the one that we're actually dealing with in this problem, which is varies jointly. And varies jointly is actually a direct variation. It simply has two values it's varying with respect to. So we still have that y equals cx like we did up there on the varies directly problem, but instead we have cx and we'll use z, for instance, here. So we have two quantities that as they change both affect how y changes. Does that kind of ring bells? It should. That's about all you're going to need for this concept, just to remember those three pieces. Those are the three pieces that you look at in variation in college algebra. So are we okay with this equation setup on the actual problem we're looking at here? Okay with that? All right. Let's see how much space I have. All right. All right, so taking a look at this one then, it actually looks a fair bit like the last problem, doesn't it? Look back up on problem number 2. Problem number 2 had that dy dx on the left, and it had x, and it had a 1 plus y. It doesn't have the c in there, but aside from that, are we good with? I mean, this looks a lot like the last problem. Okay, so tell me what we're going to do to solve this problem. Okay, multiply the dx to the right-hand side, and what else, Chelsea? Perfect. So this is going to become 1 over L minus y dy equals, I have a c and an x, and now a dx. And then I can integrate, yeah? Okay, what will the integral on the left become? There's one difference here that we didn't have happen in the last problem. What's the sign before y here? It's a negative, isn't it? The last problem it was a positive, wasn't it? That actually changes things slightly. It's not huge, but it does change them slightly, because as we're looking at this problem, this is a u substitution problem that we're not really writing the step out for. You guys recognize that, right? Because it's not a very interesting derivative of L minus y. But there is something more than just 1. On the last one, if I had taken the derivative of 1 plus y, the dy is actually just 1, right? But on this one, what do I get?
Negative.
I get a negative. So I need a negative here on the left hand, or on the outside of the natural log. So I've got negative natural log of the L minus y here instead. Okay, how about the right hand side? What do I get over here? Cx squared over 2 plus some other constant, right? So I'm starting to have a lot of constants going on. So how about I come back up here, instead of calling this c, I call it c1, and we'll introduce a plus c2 here. And we're going to see if we can't get rid of all these extra constants and sort of merge them into something similar, or something in a minute. But we've got this going on. All good? All right. So our goal, just like on the last one, was then to solve for y. So now what? We do need the e. We have to do something before that, though. We got to get rid of that negative, because in order to do the e to the power, I really don't want that negative involved. I'm going to have to either use it as an exponent then on the L minus y, which is not happy to me. I don't like that idea at all. Or I can use it directly at the beginning, and I can simply move it to the other side right now. Does that sound good to you guys? So let's rewrite this as the natural log of L minus y equals negative c1 x squared over 2 plus c2. And then I can use the base e like I did on my last problem. Okay, so on the left-hand side, there's the L minus y. Great. Boy, that's a mess on the right-hand side, though, isn't it? All right, so what can we do? Well, there's several things we can do. Unfortunately, none of them are all that sort of nice looking. That's not quite true, but some of them aren't anyway. So we can do the separation thing that we done in the last problem, right? Where we recognize that we can write this as e to the negative c1 x2 over 2 and e to the c2. Okay, so we can do that. And we can recognize that e to the c2 is just some constant number, just like last time too, right? So I've still got the L minus y on the left. I can write this as some constant c, and I can write this as e to the next part. Now here's the next thing, and this becomes very interesting, because I've got this negative, right? And I've got this c1. c1's just a constant, right? Sure. Is negative c1 also a constant? Yeah, so could I just call it something else so that I don't have the negative there? Give it another name. I mean, it's just a constant, whether it's positive or negative. I don't even know at this point because I don't know what c1 is. So I'm going to call this negative c1 something else. Your book uses a k, so I'm going to go with a k here, k for a constant. Some college algebra textbooks you'll see over here on this varies directly here, where I put all those c's, we'll put k's in here anyways. So, all right, so we're going to use a k there. So this is kx squared over 2. Still, goal is to solve for y. So what could I do? I could. I'm going to do it in a little bit of a reverse order than you suggested, Janet. I'm actually going to move the CE to this side and then the y over here, so it'll already be positive, but I'll get the same answer. So I'm going to end up moving. So this will say L minus CE to the kx squared over 2 equals y. And that is the solution to the differential equation that I started with. It's a general solution though, right? I don't know what C is and I don't know what K is. But you know what? There are problems in which we can find those out. Let's take a look at the next one. This one actually asks us to find a function, y equals f of t, passing through 0, 10 with the given first derivative. So this one has this extra sort of piece of information at the end that I've got a 0, 10. What's that going to allow me to do?
Find C.
It's going to allow me to find C. That's the difference in this problem. That's the only difference, really. So how will the problem start? Move the dt over and no division. Here, I'll do that first. I think I may have moved too fast. Can I write this as t to the 1/2? Is everybody good with that? Okay, what's next then? Yeah, this one doesn't have actually that added feature that the last two did, right? I actually do have all the variables separated once I move the dt over. So I'm ready to take the integral, you bet. Okay, integral on the left is y. On the right, that's negative 3/4. Now what? 2/3 t to the 3/2. Good. And then plus c. Let's clean this up a little bit before we start plugging anything in. I've got y equals what? Good. Negative 1/2. What is t to the 3/2? Is, say that again, Taylor?
Well, you don't do that.
How about we write it as the square root of t cubed? And because it's going to be nice in a minute potentially to do so, or it might be, you could also recognize that it's t square root of t. Either of those would be fine. Now, on this particular problem, it doesn't end up mattering much because the t value that we're given up here is actually what? It's 0, so any of these are equally nice to plug in 0 into, right? It doesn't really matter. Since the problem started as square roots, though, we probably want to have the answer in terms of square roots. So I'm going to go with the t square root of t. If you want to leave it as the square root of t cubed, that's okay. It's not really simplified, but it certainly doesn't hurt at this stage to have it like that. And then I have plus c. So now what am I going to do? Right. So y is 10, right? And t, as we said just a minute ago, is 0. So what's c? It's 10. So my differential equation is actually y equals, my solution to my differential equation, rather, is y equals negative 1/2 t square root t plus 10. And that is the particular solution for my general equation. Not so bad, right? Okay. Let's try one that kind of puts a little bit more of this together. Got a lot of information going on in this problem. We've got a proportional issue. The rate of change of y is proportional to x. We've got 2 sets of information when x equals this, y equals this. And then we've got the question asked at the end that says, all right, now using that information, what do you get when x equals 8? So there's a lot of steps in this problem, agreed? Now, the first information, though, actually tells us that we're looking at a differential equation because it says rate of change of y. So what does rate of change of y mean?
dy dx.
That's dy dx. This is starting out telling you this is dy dx equals something. It says it's proportional to. Proportional to is another phrase that means simply the same thing we did on that previous slide, which means varies directly. Which means that this is equal to c, or some c value. Let's see, I used k on my notes, so let me use k here as well. Some k value times y. Because this is a direct variation. Proportional and direct are the same kind of a variation. All right, so we start out here. You guys know what to do. We've done these problems already. What are we going to do first? Move the dx. All right, so this is dy equals ky dx. Now what? Yeah, we got to get that y moved. So this is actually 1 over y dy equals k dx. Now what?
Take the integral.
Now I can take the integral. I know there's no x's technically on the right-hand side. That's okay. What do we get on the left? Good, natural log of y. And the right? Kx plus c. All good? Okay, now what?
Use the values.
Use what was that?
The values.
Can't use the values yet.
So
Well, I mean, I guess we could use the values at this point. It wouldn't hurt anything, but it's going to simplify things quite a bit if we do something else first. The e, yeah, because we're gonna have to do that at some point anyway, whether we do it now or later. All right, so this is y equals, and this is e to the kx, e to the c. Let's call this c1 back when we did it, because I don't really want it written separately with the addition like it was. I'd really much prefer it being written as multiplication. So c e to the kx. This is the general solution to my differential equation. How many constants do we not know in this problem? 2. There's a c and there's a k. And that is the reason that we have 2 pieces of information up here, because we need both pieces of them in order to find out what the particular solution will be. One of them is nicer than the other one. Which of those 2 pieces of information is the nicer one to work with?
0.
Yeah, the one with x equals to 0. That actually eliminates, if we started with the x equals 4, y equals 15, the problem is that the values that we would get would still leave a c and an x in my problem, which means I couldn't solve anything directly. But if I put in x equals 0, kx goes away, doesn't it? So there's no more k in the problem, which means I can now solve for c. So we're going to start this problem. Let's see how much space I have. All right, so we're going to continue this problem. I'll go up here. And we're going to plug in this first set of values in for x and y. So I have 6 equals c e to the k times 0. So 6 equals c e to the 0. What is e to the 0? 1. So 6 equals c times 1. So what's c? 6. You guys did that quite well. Not too bad, right? So right now, this problem has become, instead of where it started, which was c e to the kx, I now have y equals 6e to the kx. Now I can use that second piece of information over here. The second piece of information says x is 4 when y is 5, or y is 15, excuse me, y is 15 when x is 4. So I can use those two pieces of information to find this one. So y is 15 when x is 4. So this is 4k now up here, right? Now what? Okay, let's divide by 6. So 15 divided by 6, will that simplify? Okay, so you can divide them both by 3, right? So this is 5 over 2 equals e to the 4k. Now what? Yeah, so this is the reverse of the last problems when we were working with well, the first part of this problem where we took the e on both sides. I need to actually find the solution for the k, which is in the exponent. So I need to do the inverse of the e, which is the natural log. So if I do the natural log on both sides, then the right-hand side becomes the 4k, right? And on the left, I have the natural log of 5/2. What's my last step? Divide by 4, or you could multiply by 1/4. I'm going to multiply by 1/4 just so that it's not got the double division look to it. All right, in terms of simplifying this to go into an equation, it will look very awkward if I replace the k with 1/4 natural log of 5/2, will it not? Yeah, that looks strange. And so the natural convention that we're going to use is we're going to find a decimal approximation for this. So grab your calculator, if you will. I want you to type in 1/4 natural log of 5/2, or if you want, natural log of 5/2, all of that, hit enter, and then divide by 4. And we're going to use the value to 4 decimal places, which is what your book uses. This is an approximation, but we're going to pretend after this that this is the value that we really wanted exactly. So what do you get for an approximation with 4 decimals? 2291. All right, so our problem right here becomes y equals 6e to the 0.2291 x. Does that look okay? We would be done if we did not have one more piece of question to answer, but we do. The second piece of question there, or the last sentence right here, asks us to find out what in the world is y when x is 8. So what are we going to do? Just plug in 8 for x. So this is y equals 6e to the 0.2291 times 8. Do make sure when you're using your calculator that you're very careful on this. You don't want to allow your calculator somehow to think that it's going to take 6 times the e to the 0.2291 and then take all of that and multiply it by 8. There's a couple of ways you can get around that. I know we've talked about this before. The way that I get around it is that instead of using parentheses up there in that exponent, I simply use the multiplication symbol. And then your calculator makes no question about it. So that is when you're looking at this in your calculator, you're entering this as, in your regular screen, as 6e. There's a caret, and it'll automatically put a parentheses in, or most of your calculators will. 2291, and then I use the times button and put an 8 here. If you use a parenthesis to close something out, you'll mess the calculator's understanding of what you want up. Okay. All right, so did it give you a value? All right, what did you get? 5.1, and that is exactly, we want 2 decimal places for a solution, although we used the 4 decimal points in the middle of the problem for accuracy. Any questions on that? Okay, so this actually is an example, number 5, the last one we did, an example of a growth model. A growth, or a growth and decay, depending on which one we're talking about, a growth and decay model has a function that when we have, if y is a differentiable function of t, you could use x in place of t, but the book is defining this in terms of t. And when y is greater than 0, y is equal to k, y prime is equal to ky for some k, then the differential equation solution is y equals c e to the kt. And we saw that happen, or that sort of form happen on several different problems that we worked. C is called the initial value. K is called the constant of proportionality. When your k value is positive, you have something that's growing exponentially. When the k value is negative, it's decaying exponentially, exponential decay. So a lot of you people are science people, so you're thinking about those molecules or whatever in the little petri dish, and they divide and they divide and they divide. That's growing exponentially. And then when you talk about exponential decay, one of the real common things you think about is carbon dating and things like that, where they date the age of a dinosaur bone or whatever. This formula, or this equation, y equals c e to the kt, should look very familiar. It comes up in several different areas. You should have seen it in several different math courses even now to this point. So, all right, so I'm going to show you an example of how you've seen it used before, and you're going to do a couple of examples like this as well in your homework. This is not calculus. Let me just say that. Okay, so this is where you've seen it used before. All right, we have a half-life for, is Ra radium? Does anybody know? Yeah? I get a nod. That's good. Radium 226 is 1599. Okay, so somebody tell me, you guys are better at this than I am, what in the world is half-life?
The time it takes to divide the substance in it.
The time it takes for, and how'd you say it, Jordan?
For it to decay to half.
For it to decay to half. For it to be half as much as it originally was, right? Okay, so that's what half-life is. So in this problem, if we have 20 grams now, then however long the half-life is, I will end up with 10 of it. Okay, is everybody good with that? Understanding what half-life is, if you haven't seen that in a little while. Half-life is 1599, which means that in 1599 years, 1,599 years, I should have 10 grams left. But this question is actually asking me, when would I have, or how much will I have in 1,000 years? So you should know from the get-go that the answer is going to be more than 10, right? It's got to be more than 10. So if you get an answer that's not more than 10, time to stop and figure out what you did wrong. It's got to be more than 10. All right, so we used this formula, or we stated this formula a moment ago, that this is a exponential, in this case, which one? Growth or decay? This is a decay problem. This is an exponential decay problem. I don't know C and I don't know K, but I can find them. The C is the easy one. Do you know what C is going to be? It's 20. C is going to be the 20. C is the initial amount that you have. And we can justify it in this way. We actually say we have 20 grams now, so in essence, when time is equal to 0, we know that y is equal to 20 grams. Well, if I put in 0 for t, right here, then the kt would all be 0, right? And e to the 0 is 1, so all of this becomes 1. All I'm left with is c on the right, and I'm left with the number 10 on the left, or 20 on the left. So c is going to be the number 20. I'll write that in just to show you what we did. So C is 20. So this problem, we now know that y equals 20 e to the kt. Now what I can't do is I can't plug in 1,000 yet. Why not? I don't know k. So I'm not to the point of actually being able to answer the question. This is one of those questions that you have sort of hidden steps going on, like it doesn't say to do something, but you have to do it. I have to find out what k is or I can't answer this question. What information have I not used? The 1599. And the 1599 is the information about the half-life, right? So let's use that next. We've got a half-life that's 1599 years. How can I use that to find K? Yeah, so if I let T be 1599, I don't know what K is, but let me put it after the 1599. 20 I already know. What will Y be? It's 10, because that's half the amount. When it's been 1,599 years, or 1,599 years, and I started out with 20 grams, I will now have 10 grams left. Okay, so what can I do? Divide by 20, so it's going to give me 1/2 on the left, which will always happen with half-life. When you divide by the original quantity, you'll end up with 1/2 on the left. E to the 1599K, now what? We're going to take the natural log of both sides. On the right-hand side, what will happen? Yeah, it'll be the 1599 in the K. And on the left, it'll be the natural log of 1/2. And then what can we do?
Divide by the 1599.
Right, good job, Erin. We divide by our 1599, and we will have our K value. Now, that still doesn't answer the question, but we're one step closer. So your calculator can do all that for you just fine. Natural log 1/2, hit enter, and then divide by 1599. K value to 4 decimals, what do you get? Oh, this one's a weird one. Somebody tell me what your K value is, what it says in your calculator. Let's start there.
-4.3349 times 10 to the negative.
It probably has a capital E somewhere in there, doesn't it? On most of your displays. So this is using scientific notation. You guys are all science people. At least you've had a fair number of science classes among you. So you know this notation. So what does 10 to the negative 4th actually do to a problem? I mean, do to a value? Yeah, it moves the decimal, and because the next one's negative, it moves it to the left, and it moves it to the left 4 times. Very good. All right, so we could actually get by with not having quite so many decimal places. I know we have 4.3349 here. If you want to use just the 4.33, that would be okay, because we've got something that's awfully small already because this is in scientific notation. If you want to use all these here, then that's fine too. I'll go ahead and use them since we have them on the screen. Nope, I don't have space. Okay. Let me move over here on the left. So my problem now looks like y equals, let's see if this comes up well enough. Not so good. Let's use black. Y equals 20 e to the negative 4.3349 times 10 to the negative 4th K. Sorry, not K, T. Something like that. And then we can answer the question, how much will I have in 1,000 years? So we'll plug our 1,000 in for T now, right? So we have y equals 20 e to the negative 4.3349 times 10 to the negative 4th times 1,000. What do you end up with? How much? 12.96, which is more than 10, isn't it? Oh, that's good news. At least we know that it seems reasonable. All right. I have absolutely no space to write this down. 12.96, is that what you said? Mm-hmm. That's a 9. Pretend like it looks like a 9. It's not a 0. I can't do it. I've got to make it look more like a 9. That's closer. 9.6. That's a G at the end. There's grams. Okay, any questions on this one? You've done this before. I know you have. This is without a doubt a college algebra math analysis pre-calculus concept. All right? One more question along the lines here then says, how much will I have in 10,000 years? What do I do? I just plug in 10,000 where I plugged in that 1,000 a moment ago, right? So y equals 20, e to the negative 4.33, was it 49? Times 10 to the negative 4, is that right? Yeah. Times 10,000 years. Again, being awfully careful with all that exponent that uses multiplication symbols so that you don't end up multiplying by 10,000. You'll know if you did, because things will look really weird when you get the answer that you got more than you started with. That's not good if it's a decay problem, right? Yeah, not so good. All right, did we get a value?
0.262 grams.
And we'll go with 2 decimal places, so let's go 0.26 grams. Good. Perfect. Any questions on that? Okay, so a little bit of college algebra thrown in there at the end because we're working with growth and decay models. Excellent.